Hello and welcome to the Indicio Identity Community Meetup for November. Thank you for joining us. Welcome to anybody who is new here or it's been a while. We're really excited to have this conversation today and excited that you're here. Just a couple of things I wanted to announce. First off, next month, before the holidays, Tuesday, December 13th, we will have a conversation about decentralized identity, digital transformation, and government in this meeting group as well. So we're going to be speaking with the Secretary of Commerce from Rhode Island, Elizabeth Tanner. She presented at the Hyperledger Global Forum for anybody who attended that event. She's a wonderful speaker, and she's going to be speaking and telling us about her adoption of verifiable credentials for the state of Rhode Island. And then Nancy Norris, who I'm sure a lot of folks in the BC Gov community that are here, she will be here as well and having that conversation about digital trust in the Ministry for Energy, Mines and Low Carbon Innovation for the government of British Columbia. So very excited to have those two. We also have the Minister of Justice from the government of Aruba joining us as well. So we will have three government officials to talk about their sort of championing of decentralized identity in their communities. This identity community meetup is made possible due to Indicio's public benefit mission, part of Indicio's public benefit mission. So we are really excited that we have this opportunity to help drive that mission of expanding the use, adoption, education, understanding, conversation around decentralized identity, all things identity, really. So we're really happy that we can do this. So with that said, I'll give one more plug, and that is on December 14th, before the holidays, we will be having a full webinar demonstration of Indicio Proven, and that is Indicio's open source, complete open source issuer, verifier, holder, complete trusted digital ecosystem for verifiable credentials. So if you're interested in seeing the whole kind of soup to nuts, I'll put the link in the chat and you can join us there. If not, no worries. And with that said, I will pass it along to one Daniel Bluhm to get us started. So thank you all so much. Enjoy.
All right, thank you, Helen. Happy to be here today. My name is Daniel Bluhm. I am a software engineer and team lead at Indicio. I've been in the decentralized identity space for a while, starting off in the Indy agent working group way back in the day, which then turned into the Hyperledger Aries project, and I've been around ever since. Also had the opportunity to contribute to the Decentralized Identity Foundation, both in code and as a co-chair of the Interoperability Working Group. I have my hands on a lot of things, but I spend most of my time working with Aries Cloud Agent Python. And today we'll be talking about issuing and verifying JSON-LD credentials with ACA-Py. I'll also hand it over to Peter for a brief introduction of himself before we get started.
Hello, everyone. My name is Peter Strobel. I've been associate software engineer at Indicio since July of 2021. After graduating with a Bachelor of Science in Physics from Willamette University here in Oregon, I've been working with repositories very closely linked to Hyperledger's ACA-Py, including the ACA-Py minimal example repository, the ACA-Py pickup plugin, and the Aries toolbox. And without further ado, let's get into a presentation.
Cool. So, of course, we'll be talking about JSON-LD credentials today. We'll start off with the basics, just kind of getting into what are JSON-LD credentials, what constitutes a JSON-LD credential. We'll go through a brief overview of the verifiable credential data model, so you can get an idea of what these credentials look like. Then we'll move into issuing and presenting JSON-LD credentials using ACA-Py, followed by a demonstration, and then wrapping it up briefly with discussion of the limitations of ACA-Py and JSON-LD credentials. Before I get started, I do want to give a brief acknowledgement that these are hotly contested topics in the decentralized identity community. However, it's in my personal opinion, at least, part of advocating for principles of decentralization is accepting that some people will choose to do things differently. And rather than getting caught up on which credential type is best, we do our best to see the advantages and disadvantages of each type and judge which one meets our needs and use cases. And that tends to be on a case-by-case basis. Something that matches one use case will not perfectly match another. Many of us are, of course, invested in the Hyperledger Aries and Indy ecosystems, which gives us a very mature credentialing system in the form of AnonCreds. And we do think that AnonCreds is great, but we also fully acknowledge that it doesn't meet every need and every use case. So today we'll be focusing on the technical rather than the wider philosophical debate and on how we can take advantage of both AnonCreds and JSON-LD credentials using Aries Cloud Agent Python. Feel free to send questions to the Zoom chat as we go along. If there's some really good questions that deserve answers immediately, I'll do my best to answer those as we go along. If not, we've got a lot of people from Indicio here today that might be able to answer your questions. We will try to save some time at the end for questions. So if you've really got a burning question that you want to raise, hopefully you'll get an opportunity to. I do ask that you please remain muted for the duration of the presentation, though. Okay, so what are JSON-LD credentials? So first, from there, I'll take another step back and say, what even is JSON-LD, which is a JSON, I'll get it out eventually, JavaScript object notation for linked data, or to put it even simpler, it's just a way of encoding linked data using JSON. This makes use of context objects that map terms to URIs that help us to unambiguously link data together. So instead of having something that could be ambiguous, like something just name, using linked data context, we can turn name into a full URI to something that describes what kind of name it is intended to mean. And so we have very discrete definitions of what our terms are in the form of these contexts. So JSON-LD credentials then, or what we commonly refer to as JSON-LD credentials, is probably more precisely described as an LDPVC, or linked data proof verifiable credential, which is a credential in W3C VC data model format, signed using linked data proofs. So LDPVC is one of several credential types in the wild today. Others include AnonCreds, JWTs, ACDC, MDoc, JWP, DTC, all the 3- and 4-letter acronyms you could hope for. And while we're on the subject of these credential types, I did want to point something out briefly, and that is that the unique combination of format plus cryptographic primitives, whether that's DIDs, DID methods, key and signature types, or the types of assertions that can be made with those primitives. These are essentially, the combination of these are what makes up one of these types, which also means that there can be overlap between the different types in the format or crypto primitives that are used. But it's that unique combination that form these distinct types. To kind of give you a little bit more of an example of what I mean by that, AnonCreds has not traditionally been formatted in a way that aligns with the W3C VC data model. There are several reasons for this, with the foremost in my mind at least being that the AnonCreds implementation was first implemented at a time when the VC data model had not yet reached the level of maturity that it's at today. However, there's not really strictly any technical reasons that AnonCreds credentials could not be expressed using the VC data model, besides simply inertia, in the sense that we have a lot of deployments in the wild today already. This is actually, in fact, one of the goals of the Hyperledger AnonCreds project, to bring the AnonCreds specification in alignment with the VC data model. And I expect that in the not too distant future, we'll be able to exchange AnonCreds credentials in a W3C VC data model compliant format. But since AnonCreds uses CL signatures and have significantly different requirements for generating and verifying these proofs, just being in the same format does not determine interoperability. Likewise, the VC data model also explicitly defines formatting for VCs as JWTs, even though the signatures over the claims of the credential differ significantly from signatures using linked data proofs. So there's a lot of different credential types out there, and LDPVC fits in that scope by being a W3C VC data model with linked data proof credential format. Okay, so having established what we mean when we say JSON-LD credentials, the next natural question, I think, is why should we use them? Especially when when many of us, at least, are pretty well versed in the AnonCreds ecosystem. I think this is a deeper question than it might seem on the surface. And the reasons for pursuing other credential formats could be as simple as that's what my client's interested in, or as nuanced as I want to take advantage of the ability to present credentials about a subject other than myself. So there's a lot of reasons, but to call out at least a few, the first that I've got here on the slides is the one that I just alluded to. JSON-LD credentials can be held and presented by anyone, whether they are the subject of the claims made in the credential or not. So this enables us to present authentic data about a party that is someone other than ourselves. And this may seem counterintuitive from an AnonCreds perspective, where we frequently go out of our way to ensure maximum privacy and control of the owners of the data. And certainly in the context of individuals, where privacy and control are indeed some of the most important guiding principles for our whole worldview of AnonCreds, there are significantly fewer use cases where this lack of a binding would be a benefit for individuals. However, if you consider verifiable credentials about public entities, where the claims made are also public information, I think there's some interesting opportunities that can be found there. One such example that comes to mind is delegating authorization. You could, for example, present a credential alongside your own credential, where you are the subject, that proves to the verifier that the issuer of your credential was authorized to issue that. And through that mechanism, chaining trust from a starting point in a decentralized way. This does, however, add a layer of complexity that we generally don't have to worry about in AnonCreds. If the holder is the subject of the credential, the holder must provide us an additional proof that they are the subject, usually through proof of DID ownership. And we'll look at that in a little bit more detail later on if that's unclear. Let's see. Alternatively, JSON-LD's somewhat simpler cryptography may be appealing to you, especially when you compare it to AnonCreds seal signatures. Seal sigs require RSA keys, which are large and potentially slow to generate and use in constrained environments like IoT. And there are, of course, specialized hardware modules for RSA keys, but it's unlikely that these will support CL signatures. JSON-LD, LDPVC, on the other hand, uses signatures that are more commonly supported by hardware modules. And in the IoT context, we're unlikely to really benefit from the additional privacy guarantees of AnonCreds. And so JSON-LD may be a really good fit for your IoT credentialing use case. And then finally, if you're into the semantic web thing, JSON-LD allows you to express deep semantic structures with unambiguous linking of attributes together. Though there is some heated debate on the subject of whether it's appropriate for credentials about individuals to have deep semantic connections. That's a whole other thing that I won't be touching. But regardless of how that debate shakes out, these deep semantic structures could be useful in enterprise contexts where it's a public entity whose data is locatable in a the big graph in the sky of semantic linked data. So now that we've got some background on JSON-LD credentials and how we might use them when compared to AnonCreds, let's start diving into some of the details of the VC data model and get a feel for what these look like. Since a lot of us are familiar with AnonCreds, I will draw some comparisons between the two as appropriate, hopefully to help us enhance our understanding. First of all, it is important to understand that the VC data model actually defines two different verifiable objects, which are verifiable credentials and verifiable presentations. A verifiable credential is a set of one or more claims made by an issuer, and what makes it verifiable is that it is packaged in a way that it is tamper evident, and the authorship of the credential can be cryptographically verified. Meanwhile, a verifiable presentation is data derived from one or more verifiable credentials issued by one or more issuers that is shared with a specific verifier. So a verifiable presentation is also a tamper evident encoded value as a presentation, which likewise has the same cryptographically verifiable authorship characteristics as verifiable credentials do. So let's digest that just a little bit further. What does it mean to have two separate verifiable objects? It means that the value received from the issuer is not the exact same value shown to the verifier. It could be, but generally it will be some value that's derived from that, or at least annotated with additional attributes to help the verifier obtain the proof that it was requesting. Believe it or not, we are actually already used to this split between credential and presentation in the AnonCreds world. We receive a credential from the issuer, and then every presentation made from that credential is actually a derivative and not the actual credential itself. So in AnonCreds, this enables us to do selective disclosure, compositing multiple claims from different credentials into a single proof, and present predicates on claims rather than revealing the original value. The separation between verifiable credential and verifiable presentation in the VC data model allows for the same set of functionality, though to my knowledge, there are only a few examples of this so far, with one of those being the selective disclosure with BVS Plus credentials that we'll be demonstrating later. Then additionally, the verifiable presentation allows the holder to present additional proofs to the verifier, such as a proof of DID ownership to help form that holder subject binding in the credential. Each VC data model, each VC data model compliant credential, whether that be a LDP VC or another type, has at least these basic ingredients to it. A context, which is a JSON-LD construct that we will look at in a little bit more detail. A type, which identifies the type of the credential, such as passport or driver's license or ice cream truck loyalty card. An issuer, which identifies the issuer of the credential. Issuance date, again, self-explanatory, but it defines when the credential becomes valid. The credential subject, which contains the actual claims of the credential, the actual interesting pieces that make assertions about the subject of the credential. And then we have a proof, which contains all the cryptographically verifiable evidence and associated metadata that the claims made in the credential are from the issuer. Okay, so first of all, the context property. So to those learning about JSON-LD for the first time, this is easily the most arcane aspect of credentials adhering to the VC data model. The context of JSON-LD credential, found in the @context property, enables the shortening of long, unreadable URIs into something that's a little bit more human-friendly. So as we discussed earlier, if we had name, the context allows us to map the string name back to a full URI where we can find documentation about exactly what kind of name we're talking about in that context. In my mind, I kind of relate the context back to a dictionary of terms, and then borrowing further from the analogies made in the VC data model specification. In order for two people to have a coherent conversation, they need to be speaking the same language where the words mean the same things to both parties. That's how you convey meaning. And this is what the context essentially defines for a given credential. These contexts are ordered sets containing URIs to resolvable contexts or to objects defining a context. And then finally, the context property must be present even if the processor does not explicitly use it. And the first item in the ordered set of contexts must be the core context of W3.org 2018 credentials v1. So JSON-LD credentials do not require schemas in the same way that AnonCreds credentials do. However, there are some similarities between JSON-LD credential contexts and AnonCreds schemas. In JSON-LD creds, the context defines the terms used in the credential, and this happens to include both the attribute names of the claims as well as the type, issuer, issuance date fields that we're talking about as being core to every credential. On the other hand, AnonCreds schemas only define the attributes or claims of the credentials they describe. Context must contain all terms used within a credential. And where we have multiple contexts, which most credentials will have multiple contexts, but the contexts are merged together. You take the union of all the terms and values used with, I think, the rightmost context in the ordered set taking precedence if there's any conflicts, collisions. And then if you have a term that's contained in your credential that is not found in that union of all the contexts, the resulting credential is considered invalid, or at least invalid JSON-LD. Similarly, in AnonCreds, all attributes found in a credential must be found within the schema. And however different from JSON-LD contexts, AnonCreds schemas are, of course, only possible with a single schema. You can't join multiple schemas together. Finally, JSON-LD credentials need not exhaustively include every term defined in its context. In other words, the context does not express that a particular term is optional or required. It merely defines the terms. In my mind, going back to the dictionary analogy, if we have a dictionary of terms, not every sentence that we form needs to contain every single word in the dictionary. Additionally, the dictionary doesn't actually define grammar or contain grammar. It just defines the terms that can be arranged according to grammar to form something with meaning. AnonCreds schemas do completely define the expected attributes of a credential, however. So in other words, if a credential is missing an attribute that's defined in the schema, the credential is considered invalid. Let's see. So neither JSON-LD context nor AnonCreds schemas actually define the data types of the values of the claims contained in the credential. This was actually a bit of a revelation to me when I realized it. I had the incorrect perception that the JSON-LD contexts went further than they do and described the values associated with the attribute names, but that is not the case, as it turns out. It merely defines terms, and then if you do want to more strictly define data models or data types of the claim values, the VC data model has a separate optional parameter for linking a JSON schema object that can then be used as a validator for issuing or receiving credentials according to that schema. We won't be looking at that today, though, the JSON schema bit. Okay, so next we have the type property. I saw the question in the chat. I think it was a very apt one, actually. The type property is what expresses the kind of verifiable credential that we're considering, and this helps the processor determine if the object provided is appropriate for its goals. Every verifiable credential has at least one element in this type array of verifiable credential, and optionally you can specify more specific types. In practice, especially in ACA-Py, it is actually required that there be additional types beyond the core verifiable credential. On the other side, verifiable presentations require a verifiable presentation type and optionally other more specific types in the same way as verifiable credentials do. Off the top of my head, I don't remember exactly if that was required in this context, but it is definitely required in the context of issuing a verifiable credential. It must include an additional type. This is pretty self-explanatory, I think, pretty direct. We have the issuer property. This expresses, oh, actually, now that I think about it, I just had remembered something I wanted to call out here. The type property, again, drawing analogies to AnonCreds, the type property is in some ways similar to the name of a schema in AnonCreds. It doesn't actually define the attributes associated with it. It just names it and gives us a value that we can use to determine or to express what sorts of values that we are interested in. Okay, sorry, back to the issuer property. This expresses the issuer of the verifiable credential. This must be present, and it must be either a URI or an object containing an ID property, which is a URI. Generally, this will be the DID of the issuer, which subsequently enables resolving the machine-readable information that is used to verify the credential, like a DID document, which contains verification material. This property is analogous in some ways, at least, to including a credential definition ID in credentials issued using AnonCreds. Issuance date, pretty straightforward. The time at which the credential becomes valid. This must be expressed as an XML datetime string. And then the credential subjects. This contains the actual claims about one or more subjects. And so you can have multiple sets of credential subjects, which can each have their own independent IDs, identifying different subjects and different sets of claims. The credential subject property must be present, and it will generally include that ID to help with, actually verifying that the holder of the credential is the subject of the credential, as we've hit on a number of times already. In AnonCreds terms, we would generally call these credential attributes, but yeah, same difference here, I guess. Then finally, the proof property. This enables the verification of claims expressed in the verifiable credential. At least one proof mechanism and the details necessary to evaluate the proof must be present. A minimal proof will at least make it possible to detect tampering and verify the authorship of the credential or presentation. It could do more, such as allowing you to selectively disclose or provide other proofs, perhaps proof of non-revocation, those sorts of things. But each proof object must contain a type property specifying which method was used to generate the proof, which then, of course, helps us to verify it later on without having to guess about types or anything like that. The properties included alongside the proof will vary according to the type of the proof. So in a hypothetical world where we already had AnonCreds expressed as VC data model objects, the proof for AnonCreds would look quite different from a proof of type 825519 signature suite 2020 or whatever it is. Okay, so to wrap up our exploration of the VC data model, just wanted to show a couple of quick examples of these verifiable credential values. We'll look at more examples as we go through our demonstration, of course, but just wanted to give a general feel for what these look like. We see our context, we see an optional ID, the type that we discussed, issuer, issuance date, credential subject with ID, and then claims made about the credential subject. One thing that is a little unique about LDPVC, JSON-LD verifiable credentials, is that the claims made in the credential can be more complex objects than simple string values, as is kind of a limitation that we have in the AnonCreds world. So we can express trees of data as opposed to just flat normalized data like we generally have to do within AnonCreds. And we'll see later on as we look at presentation definitions that we have to be able to address these credential values by walking through those paths as well and down each limb of the tree. We'll get into more details on that. And then it will, of course, include a proof. I've omitted the values here. We'll look at the concrete examples in our demo. And then to contrast with the verifiable credential, this is what a verifiable presentation looks like. Again, it has a type, an ID, and a context, and then a set of verifiable credential objects and a set of proofs. And with that, I will hand it off to Peter to take us through some of the details of issuing JSON-LD credentials with ACA-Py specifically.
Thank you very much. I'm gonna steal screen share here. And perfect. Okay. So wrapping up the VC format discussion, let's get to actually talking about how we use JSON-LD credentials with ACA-Py. Double checking, you can all see pretty much the exact same slides, right?
Yep.
Excellent. Okay. So turning our attention to the implementation of JSON-LD credentials in ACA-Py, It's important to keep in mind that the original V1 protocol for credential issuance and present proof are not compatible with JSON-LD. Fortunately, for those who are using AnonCreds and issue credential version 1, though, you can present credentials issued using V1 with either V1 or V2 of the present proof protocol. Unfortunately, that means that in order to use JSON-LD credentials in your agents, on top of adding support for the JSON-LD credential type itself, you'll also need to add support for the version 2 versions of both protocols. ACA-Py does support both protocols, but you will have to adjust your own controllers to use the new V2 endpoints to take advantage of them. We will discuss some of the differences in protocols in the admin API of ACA-Py in just a moment. So with compatibility constraints in mind, let's take a look at how to actually issue JSON-LD credential with ACA-Py. Now, the issue credential version 2 protocol should look pretty familiar if you know V1. The protocol works through a message exchange between two parties, the issuer and the holder, which in a real life scenario could be a government and someone applying to get a passport, for example. The overall message flow has not changed from V1, but there are some short circuit paths that are not possible when using AnonCreds that are when using JSON-LD credentials that are worth briefly calling out here. The holder can initiate a credential exchange by directly sending a request credential message instead of starting from a proposal. Now, if there's no cost to make the holder aware of, when issuing a JSON-LD credential, we can entirely skip the proposal offer cycle and proceed straight to the requesting a credential. Now, in AnonCreds, the issuer must inform the holder of some crucial cryptographic information before the holder can send a credential request. This meant that if the holder wanted to initiate a credential issuance, it must do so with a proposed credential message, triggering the required exchange of cryptographic information in the offer credential message from the issuer. This is not the case with JSON-LD, however. If negotiations are required, then this must be done with the proposal and offer messages still. Moving on. Aside from the short circuiting differences possible with JSON-LD, there are some notable message specific differences. First, to summarize all the changes made in a few words, the issue credential V2 protocol corrects values and structures in V1 that were strongly influenced by Indy AnonCreds. Now, there were efforts in the V1 protocol to accommodate other credential formats, but ultimately, there were shortcomings that made doing so infeasible without making major modifications. Hence, we now have V2. For example, in V1, the credential preview object contains several filters like schema name, schema ID, credDef ID, etc., that generally only apply to AnonCreds. In V2, the credential preview object has been further generalized and are considered attachments with separately defined formats. Now, there are multiple filter formats linked from the RFC's registry of such formats, including DIF credential manifests, Indy credential abstracts, and linked data proof VC detail. Linked data proof VC detail is the format that we'll be using during our demonstration later. Now, finally, I was trying to figure out where to position all the cameras. Excuse me. Finally, issue credential V1, the protocol did make credentials attachments, which were intended to allow for the flexibility in credential formats, but sadly and fatally, this did not include any indication of the format of the credential included in the attachment. Now, V2 defines formats in a similar fashion to the filters used in credential previews for the final credential values as well. The registry of formats linked to the RFC include the linked data proof VC and Hyperledger Indy credential. Now, there are some notable differences between V1 and V2 versions of the issue credential API for ACA-Py. For example, here's a side-by-side of the comparison of the issue credential send endpoint with issue credential V1 on the left and V2 on the right. On the left, we see that the Indy specific attributes of schema ID, schema issuer, schema name, schema version, cred def ID are included at the root level of the request body. Whereas on the right, we see these values have been nicely organized into the filter Indy object. Looking a little bit closer, we can also find that the credential proposal object on the left has now been renamed to credential preview on the right. Finally, we see that the addition of the LD proof, filter object, which contains a credential and options properties. The LD proof object is defined by Aries RFC 0593. You can find that the format of these values is very similar to the VC HTTP API. However, it does differ in a few key ways. Now we'll be looking into V2. We'll be looking to V2 API in a little bit more during our actual demonstration. Moving on, let's take a look at how we actually present JSON-LD credentials in ACA-Py. So the present proof protocol, V2, is a general purpose verifiable presentation exchange protocol, meaning that it can be used to present credentials in any format. I mean, granted that your agent supports these formats. Now, as with issue credential protocols, if you're familiar with version 1 of present proof, then version 2 should look very familiar. As a quick review, most presentation exchanges are initiated by the verifier by sending a request presentation message, but the prover may also start the exchange with a proposed presentation message. The protocol then supports a negotiations phase where the verifier and prover can repeatedly exchange counter proposals and requests until the prover is willing to present proof of the requested attributes. It's kind of like trading properties in Monopoly until everyone gets a very beneficial exchange. Now, to do so, the prover sends a presentation message and the verifier finishes exchange with an acknowledgement message, which you can see at the very bottom of the flow on the right. Now, as with the issue credential protocol, the present proof protocol required changes to better enable exchanging presentations in various formats. The original V1 protocol was, again, heavily influenced by Indy and AnonCreds, which resulted in some Indy-centric values and structures in messages of the protocol. Now, even though presentations were delivered as attachments, this gave the V1 protocol a very distinct Indy flavor. Version 2 of the protocol was changed in very similar ways to V2 of the issue credential protocol. So in each message that used attachments for delivering presentation objects specific to a given format, an explicit formats field was added to help identify the type and versions of the attached objects. Now, each message also has an associated registry of objects for exchange in the attachments. For example, the presentation message, the registry contains definitions for DIF presentation exchange, submissions, and Hyperledger Indy proofs. As a natural result of now supporting V2 of the present proof protocol, and with the addition of support for linked data proof VCs, the admin API for requesting and fulfilling presentations has also been changed from V1 to V2 in ACA-Py. The most notable change, as shown here, is that the Indy specific attributes that we see on the right are now nested under an object called Indy. Alongside this object, we also find a new object for specifying presentation requests in DIF format, which is called presentation definitions. We'll also go over the differences in more detail in just a moment. Now, there are a few other minor changes to take into account, such as that proof requests object from V1 is now presentation requests in V2. Going into just a little bit of the JSON-LD presentation definitions, we won't be going over this super in depth because we will be seeing these again in our demonstration. But the presentation definitions of JSON-LD are just objects that help articulate what proofs a verifier is requesting from the holder, and they help the holder decide how and whether to interact with the verifier. It is composed of inputs that describe forms and details of required proofs. Like for instance, you see in the constraint check section, there's a field subsection which requires some kind of date of birth, which means that whatever credential is being presented from the holder to a verifier, it does need to include date of birth. Now, this, of course, this is not going to allow the holder to specify to selectively disclose this information about, I don't want to give them my exact birth date, but I might want to do like, I'm above this age. This does not do that, but we do have signature suites that do that for us. Going over just a few of the components broadly, we see the necessary components that were seen in the previous slide on the left, such as the ID and the input descriptors. And there are a couple optional components on the right, such as the name, what you want to name the presentation, what is the purpose of this presentation, why are you sending it over to the verifier, the format the presentation should be in. And there are many, this is not a comprehensive list. There are many, many, many other optional things you could add into a presentation. And I believe also some custom definition that you can add in too. Should there be something that is not, that you would want to include yourself that's not specified anywhere else. A couple of things about some of those items. We saw previously one of the necessary components was in is holder object for your input descriptors, which just specifies that the holder must prove that they are the subject of the claim associated with the constraint, and which is also necessary for linked data proof VCs because the lack of holder binding. There's also a limit disclosure option, which specifies that the holder will selectively disclose claims and won't include claims that were not explicitly requested by the verifier. Now, in order to use selective disclosure with JSON-LD credentials and ACA-Py, both the issuer and the holder are required to have BLS keys. And that is an overview of JSON-LD credentials in ACA-Py. Now let's get over to the incredibly fancy demonstration. I will give back screen share.
Thanks, Peter. I'll get my slide shared back here for a minute. Okay, so before we jumped into the demo, I did want to give a little bit of preamble, a little bit of orientation to what we'll be seeing within the demo. We are going to be using a project that is maintained by Indicio called the ACA-Py Minimal Reproducible Example. It's a template repo, so you can not only clone it, but you can also generate other GitHub projects from it, which is quite handy. And we use this to reproduce scenarios with the minimum set of requirements while clearly showing the admin request being sent to the agents and the webhooks being received from the agents. So it's basically a way of doing a very quick demonstration of a feature or problem. And that's how we tend to use it at Indicio. You can find a link to the branch that I'll be using. So if you clone this, make sure you check out the demo JSON-LD branch. And then if you'd like to run the example yourself, you can do so with a simple Docker compose run example. Don't forget to down the containers after the fact. They will be left running in the background after this program exits. So if you're like me and you get a little compulsive about those sorts of things, make sure you do a Docker compose down. So there will be 3 services that are started up by the Docker compose script that we'll be using in the example. One is the example service, which acts as a controller. The Alice service, which will be acting and fulfilling the role of issuer and verifier. And then a Bob service, which acts as holder and prover. The controller will send admin API requests to either of the agents in order to orchestrate a scenario between the 2 agents. Controller then receives webhooks over WebSocket back from the agents. And this helps the controller to take the correct action at the correct time and helps us know when asynchronous exchanges occurring between Alice and Bob have completed, so we can trigger the next step in the exchange. And then finally, Alice and Bob are exchanging DIDCOM messages. And that's the only interaction taking place between these two services is over DIDCOM. Okay, and now I will switch over to my demo. Do a little bit of screen juggling here. There's my window. Okay, I'll do a quick double check on font size. Is that legible? I can increase it. I'll go ahead and increase it. Okay, so I am in the ACA-Py minimal example project where I have it locally on my machine. I am in the demo JSON-LD branch, and I will now run the run example right here. So there's going to be a lot of output in just a second. And I will pause throughout, point out a few highlights along the way, and then proceed with each of the examples that we've prepared for you. Okay, so for this first section here, the issuer and recipients are preparing for a credential exchange. So if I go all the way back up to the top, we see that it started off a little further. It started off by establishing a connection between the two agents. This was done with a bog standard DID exchange with out-of-band invitations exchanged between the two agents. If you're interested in viewing each of the steps along the way, each of the admin API requests, as well as the webhooks that are sent back to ACA-Py in this process, those are all visible in the output from this example script. We'll skip past that though for now. And then we prepare for issuance by first having the issuer prepare the DIDs that it will use to issue the credentials. We will be issuing 3 different credentials, 2 with ED25519 signatures, using DID-SOV DIDs as the issuing DID. And then we will do one that is a BBS Plus credential using a DID key with a BLS key represented in it. So in order to get that DID-SOV method on the ledger, we need to go through a bit of a process of transaction author agreement, onboarding onto the network, which I've all automated here since we're using the Indicio, I believe DemoNet is the one we're connected to right now. We do some transaction author agreement stuff. Again, this isn't the interesting part really of this demonstration, so I'll skip past it a little bit, but we've created a public DID, we've set it as public, and it is now ready for issuing credentials from that DID. We will also create a BLS key, and this will be used as the issuing key for a BBS Plus credential. On the other side, the recipient will also prepare DIDs that will be included in the subject of the credentials issued by Alice. Or our issuer. The ED25519 keys could be the same keys that are associated with a connection. It could be other values. Usually it'll need to be something that you can prove ownership over. And if that's a peer DID, you'll have to provide proof of ownership over that peer DID, which gives multiple verifiers a correlating vector. So it might not be ideal in your use cases. This is actually one of the limitations of JSON-LD holder binding presentations. But yeah, just to keep that in mind. We also need to create a BLS key specifically for the holder to receive a BBS Plus credential. And that is actually because in order to prove ownership over a credential where we're selectively disclosing information and then also providing proof of ownership over that credential, we have to be able to do BLS signatures. We'll jump on to the next step now here. Again, a lot of output. I won't go through all of this, but I'll go to, let's see, a few interesting points. This is a credential exchange taking place between Alice and Bob, where this is the request that Bob is sending to Alice. Had to think that one through for a second there. So the credential that Bob is ultimately requesting here looks like this from this point to that point. So we see the context as we normally do with JSON-LD credentials. We see our credential subject. which in this case includes the birth country, birth date, family name, gender given name of Bob. This context is using the core context and an example context that's included alongside the VC data model just for demonstration purposes. We see our type, which specifies that this is a permanent resident credential. Let's see, what other key points here? The ID is also included in the credential subject, which identifies a key that Bob owns, so he can prove that he is the subject of this credential later on. And we also see our did solve issuer did in here. This can be resolved later for verification purposes. And then we also have specified that the proof type of the resulting issued credential should be a 825519 signature. Let's see, let's find the final credential value to take a look at here, which will include our proof. That's our offer request cred issue. Must have missed it. There we are. So after signing, our credential turned into a verifiable credential and now includes a proof, which has a JWS signature in linked data proof style that includes headers. The signed payload, which would normally exist between those two dots in a JWS, is considered an external value that is reproduced in a specified manner for linked data proofs, and then the actual signature value included there. We see that it specifies a verification method, which points to did solve, and then the verification method identified by key-1 as the ID. And the type specifies that it's an 825519 signature. Okay, I'm going to go a little faster through some of these other bits here. That was next a presentation exchange occurring between Alice and Bob. And we have a summary of that presentation after it took place. We see that it verified as true, so the verification of the credential was successful. We were able to see the values were cryptographically verifiable as being from that original issuer. We can look at our presentation definition here. So this was what was sent from Alice, acting as the verifier, to Bob, who was acting as the prover. We see options, which include a challenge. This makes it so the presentation is not able to be replayed, if I understand correctly, at least. Domain, can't say what that is off the top of my head, sorry. Then we see the presentation definition that Peter was just describing a moment ago. So we see that we specify that we want a presentation with a credential, with a proof type of 825519. We also specify the format type of the credential that we're requesting, which in this case was an LDP verifiable presentation. Then we specify input descriptors and a set of constraints for those input descriptors. So in this presentation definition, we are explicitly saying that I, as the verifier, am looking for a credential where the given, or the family name rather, is builder in the credential. That's kind of an odd constraint to place, but you can. In this particular context, we can specify a purpose, and then we specify the path to the attribute within the credential, which in this case is credential subject family name. We can do the same with other values, of course. So we've got another one here saying that I'm looking for a credential that contains given name, and then is holder specifies that we are requiring that they prove that they own the did that was included in the subject. And then we see the proof as given here. So this is a verifiable presentation, contained a set of verifiable credentials, in this case, just the one. We see the original proof from the issuer inside. And then alongside that, we have a presentation submission, which helps the verifier map the presentation definition to this specific presentation that is being submitted to the verifier. And then we see the proof, which is signed by the ID of the credential subject. And this is our holder subject binding proof here. Okay, I need to move a little faster. So we've just done another 825519 credential issuance. Let's go ahead and move on to the presentation. And then I'll go back and take a closer look at the credential that was presented, which had a couple of custom values. So in this case, we're using custom context objects. And in this particular one, it's embedded directly within the credential. As far as I know, this is actually a discouraged practice. It's not recommended that you directly embed contexts into your credentials. They should be published somewhere where there's at least some level of permanence to them. But for the sake of demonstration, I've included the context here. And this is a pretty minimal context, which defines just two things, the table tennis tournament win and the date one claim. We use that table tennis tournament win as the type of the credential that was issued. Where is that? There it is. And the date one as one of our claims in the credential subject. Yeah, let's go on from there. And then finally, we'll do a BBS plus issuance, which just took place, and then we'll move on to the presentation. And then I'll briefly call out what our presentation looks like when we have selective disclosure. So here's our verifiable presentation. We had an employment credential. We only wanted them to disclose their clearance level. So that's what is being expressed in this presentation definition here. We also included the as holder directive, or constraint, I should say, which requires that the holder prove that they are the subject again. And we explicitly required them to limit disclosure. So we don't want to see any of the other values contained within that credential, just the clearance level. So this credential included some other values, date of employment, I think, date of hire, whatever it was. But we only see the final clearance value included here, and then a proof that it was derived from the signature over that credential value. Oh my goodness, we're out of time. Okay, so there's a lot more detail that you can look at there in the demo. If you want to run that yourself, I need to go back and wrap it up with some final thoughts on some of the limitations that we are currently experiencing within ACA-Py and within JSON-LD credential ecosystem. So first, only ED 25519 and BBS plus signatures are supported, which is a bummer. Also, there's only strictly support for issuing from DID-SOV and DID-Key. However, you can verify from a wider range of DID methods if you plug in something like a universal resolver into your ACA-Py instance. There's also no built-in support for credential status or revocation lists. There's no built-in support for validating a credential against a credential schema, as we talked about a little bit earlier. And then finally, there's not really right now a very clean way of exchanging those BLS keys that we identified as being required for both parties in order to issue BBS plus credentials. When we eventually end up in a world where we have things like DID Indy or support for other DID methods within ACA-Py, where there's more flexibility in what values can be written to the DID document, we will have the ability to specify BLS keys inside of those DID documents, which should help us solve this problem. And then finally, the integration in ACA-Py could be cleaner, not to throw shade on anybody who's contributed to this implementation in ACA-Py, but could be better library support, could be a little bit more flexibility in DID method and signature suite support. Finally, some limitations to JSON-LD in general. Complexity, I think, is one. If you're unfamiliar with JSON-LD, wrapping your mind around contexts can be a bit of a jump. It certainly was for me. And this is kind of again, hot button topics here. These are hotly contested as recently as IAW and other forums, I'm pretty sure. But then in addition to the complexity of just understanding JSON-LD itself, we also need to worry about the immutability and availability of those contexts. If you have a context that's been published somewhere and then suddenly it's unavailable, you now have a much harder time verifying that the credential is what you expect it to be, and it effectively voids the credentials associated with that context. In fact, as I was going through preparing the demonstration for this presentation, the W3 .org credentials core context actually became temporarily unavailable, and my issuance and presentation failed as a result. Granted, the spec explicitly states that you should statically store those and cache those locally. It's still a problem if you need to dynamically retrieve any context at any time. Zero knowledge proof predicates are not possible with current signature suites, and the holder binding, which can be a benefit, is not directly included as part of it. We have workarounds, of course, in the form of proving data ownership, but yeah. Okay, thank you. That was a lot of information. I appreciate those who participated and followed along. Apologize we didn't have enough time for questions at the end here, but if you want to reach out to us at Indicio, we are more than happy to answer questions and help you do what you want to do with ACA-Py.